Hi everybody, Mr. Judson here. So we got one more day to spend in Chapter 7, Section 2. And the goal today really is to just push this idea of rotational volumes a little bit farther using things like trig functions, e raised to some exponent, natural logs, maybe graphing an arc trig function. Don't worry about the graphing part. You can always use your calculator to graph those. We just need to know what the picture looks like and then proceed from there. So really not that much different than what we've done, but using some equations that are a little different. So let's start with this one. All right, so here's the problem we want to work with. We're going to take the equation y equals square root of x minus 2. It's just a square root function that's been shifted to the right 2 units on the interval 2 to 6, and we're going to rotate that about the line x equals 1. I should also say that this is bounded by y equals 0, which that's the x-axis. So we're taking the area underneath this curve down to the x-axis on the interval 2 to 6, rotating that about where x equals 1. You guys go ahead and try that. Okay, so first I want to graph this function. 1, 2, 3, 4, 5, 6. So we're taking the interval from 2 to 6. My square root function would look like this. And I want to rotate that about this line, x equals 1. So what I'm going to get is, let's see, this point when I rotate around would be right here at the origin. This point here at 6 would be 5 units away from 1. So I'd have to go back, I'll just put it right here, to negative 5. And so I'm going to have a picture that looks like that. Well, maybe a little bit larger, but we'll work with it. And so it's hollow in the inside. That means we're using the washer method. So let me draw one washer. Here's the hollow part. And because my thickness runs up and down, that means we've got dy, and so everything needs to be in terms of y. So if I was to take 6 and plug that back into here, 6 minus 2, that would be 4. The square root of that is 2. So this is the point 6 comma 2. And so that means as I stack these washers on top of each other, they're going to start down here at y equals 0 and go as high as y equals 2. So I've got the integral from 0 to 2. Pi times that, we're going to have big radius squared minus little radius squared dy. And so now I just have to figure out what am I going to call those two radii. Now remember, when you draw the radius, you always have to draw it to the original function. This is the original part out here. So my large radius is going to start right here and go all the way out to this line. So as you move this point up and down your axis of rotation, it doesn't change. It's always at 1. As you move this up and down, it doesn't change either. It's always at x equals 6. And so my radius there, remember what we did in the last video? Larger number minus smaller number. So 6 minus 1, that means that radius is always going to be 5. So that's my large radius squared. So I've got the integral from 0 to 2. 5 squared is 25 minus what I get for the small radius. Alright, so the small radius goes from our axis of rotation out to the original function. So when I look at this, I got to think, okay, we're going horizontal. That means x values. So whatever this x value is, minus 1. Because this is always at x equals 1. This point's going to change as you move along the curve. And so I have to have a variable in there. So my small radius is going to be x, whatever the x value is, minus 1. But I don't want this in terms of x, right? I want this in terms of y, and so what I need to do is I need to go up here and solve for x and see what I'm going to substitute in to this equation. So let's see, if I square both sides, I'm going to get y squared equals x minus 2. And then if I move that 2 to the other side, I've got y squared plus 2 equals x. That's what I want to put in place of this x right here. So now my little radius is going to equal y squared plus 2 minus 1. Or just y squared minus 1. So if I put that in here, I've got y squared minus 1. Oh, I'm sorry, plus 1. And I have to square that. And then dy. All right, that's a 2 and that's a 2. So if we want to simplify things in order to do this integral, we could do that. Or you could just punch it in the way that you see it there. I'll just go ahead and punch it straight into the calculator. So I've got pi times the integral. If you get any error messages on here, put a multiplication sign between pi and the integral. Sometimes that makes a difference. 25 minus, in parentheses, I've got y squared plus 1. And then I need to square that with respect to y from 0 to 2. And the answer that I got, this is our volume, is 544 pi over 15 cubic units. Now, remember, this answer doesn't make a whole lot of sense to us. If you want this as a decimal number, all you got to do is go back and put a decimal number somewhere in our integral, and then we get the decimal equivalent. So this would be 113.935 cubic units. Either one of those are good answers. All right, so here's another problem. This time we have a region that is bounded by square root of the sine of x, y equals 0, x equals 0. That's just the x-axis and the y-axis. And x equals pi over 2. And we're going to rotate that about the x-axis. So the first thing I need to do is I need to see what's the region look like that we're trying to rotate about the x-axis. And again, use your graphing calculator to graph this. We've never graphed the square root of a trig function. I kind of think I know what it's like, but I'm not sure. So go ahead and try that. Let's find that region and get our picture set up, and then we'll do the integral. All right, so here's what that graph looks like. We know what a sine curve looks like. When you take the square root, I know at the highest point the sine equals 1. The square root of that is just going to be 1, so it really doesn't look that much different. Over here we're taking the square root of negative numbers, and that's undefined. But we're not even going to get that far because, you know, this is at pi. Pi over 2 is only half of this region. And so here's what that graph looks like. We're going from 0 to pi over 2. And from y equals 0, which is the x-axis, up to this curve right here. So we're going to take this region and rotate it about the x-axis. So I'll get another section down here. Once again, this looks kind of like a sideways bowl. It's solid all the way through. It's not hollow. So that means if I'm trying to choose between the disk method or the washer method, I want the disk method. The washer method you only use when something's hollow inside. So here would be a disk. My thickness runs in the x direction. And so what I have is pi times the integral from a to b of r squared dx. Right? Disk method. It's not hollow, so we're not subtracting the little radius squared. So this would be pi times the integral from, we're starting at 0 and going to pi over 2. My radius here is going to be from my axis of rotation up to the original curve. And so that radius really is just the y-coordinate right here, y minus 0. The y-coordinate here would be 0. So radius equals y. We know y is equal to the square root of the sine of x, and so that's what we want right here. So if I square a square root, I come right back to this. I know a lot of people are thinking, yeah, let's just punch that in the calculator, but we should know the integral of a sine of x, right? We did that on our formula test. This would be a negative cosine of x, evaluated from 0 to pi over 2 times pi. And so if I plug that in, I've got pi times a negative cosine of pi over 2 minus what you get when you plug the 0 in, which would be a negative cosine of 0. And the cosine at pi over 2, think unit circle, value of the cosine right here is 0, minus value of the cosine at 0, that's right here. Cosine is the x-coordinate, so that's 1. So I've got minus a negative 1 times pi. And so really I just have a positive 1 times pi. I'd be a little nervous if this came out to be a negative answer, because how do you get negative volume? You can't. That should never happen on any of these problems. So our volume equals pi cubic units. All right, there it is. All right, so we've got one more problem here to look at. I'm not going to lie, this one's going to be a little more challenging, but I think it's a good one to look at. They want us to verify that the volume of a cone is volume equals 1/3 pi r squared times h. You know, we've always thought of a cone as the volume equals this, base times height over 3. Well, capital B means the area of the base, and the bottom of a cone is just a circle, so we're doing pi r cubed for that circle, and then dividing by 3 is the same as multiplying by 1/3. So we're really trying to verify that this is true. You know, if you think back to geometry, this is a pretty hard thing to verify. You know, probably in geometry our teacher said, well, there it is. There's the formula to find the volume of a cone. Let's go with it. But we don't really know for sure that it's true. Well, of course we know it's true, because otherwise they wouldn't have told us. But we've never had it proven to us. And so that's what we're going to do here today. So to start, I need to draw a picture of a cone. And so what I'm going to do is I'm going to say, let's just call this the height of the cone, h, whatever it is. My cone comes down like this. We know we have a circle at the base. And so to get this, what I really did is I just took a right triangle and I rotated it about the y-axis. Does that make sense? We took a right triangle right here and we rotated that about the y-axis. And so this point right here we would call the radius. So as a point, that would be r comma 0. This up here would be 0 comma h. And so what I need to do is I need to find an equation for this line that I'm rotating about the y-axis. Well, it's just a straight line. It's got a y-intercept of h, so I'm going to think down here y equals mx plus b. My y-intercept is just that h value, so y equals something times x plus h. The slope of this line is to go down h units and over r. So a negative h over r, that's what needs to go right here. Y equals mx plus b. There's my slope, there's my y-intercept of this line. Okay? And I'm going to rotate that about the y-axis. So this sounds like a disk method. It's not hollow. It's a solid cone. So I have a disk that looks like this. My thickness is running up and down in the y direction. So, a lot of times we get a problem like this and we try to think through the whole thing and know exactly what to do. I don't do that. I just take one piece at a time. One little piece. What's the picture look like? Okay, what was the equation that just got rotated around something? What was it rotated around? Is it a disk method or is it a washer method? Now the only thing I'm thinking is if it's disk method, I've got volume equals pi times the integral from a to b of the radius squared dy. That's all I'm thinking. So my next step is, what are my a and b values? Well, you guys think about this for a minute. If I stack these disks, they're going from what to what? From 0 to h. So my integral is now pi times the integral from 0 to h. I've got something squared, and I just know I want it to be in terms of y. So what I have to remember here is r is a fixed value, and so is h. I mean, I know we can change that and have different heights and different radii for a cone, but for right now, for this problem, these aren't changing. So I just need to think of those as constants. And my radius here is going to start at the axis of rotation and go out to that line. And so really it's just whatever the x-coordinate is at this point. So I need to solve this for x. Alright, so I'm going to move this term to the other side so that it becomes positive. I'll move the y back over here so that it becomes negative, so I've got h minus y. And then to get x by itself, I just have to move this fraction over and divide. And to divide by a fraction, you really multiply by the reciprocal. So h minus y times, flip it over and multiply, I got r over h. There's what x is equal to. That's the radius that needs to go into here. So if I put that in there, I've got h minus y times r over h. Well, let's work through this. Pi times the integral from 0 to h. I have to square everything inside of here, so I'm going to square this first. So what I'm going to get is h squared, multiply the 2 and double it, you get minus 2hy, and then you square the last term, plus y squared. And then I also need to square this. RH times r, or r over h times r over h is going to be r squared over h squared dy. So if I had to solve this integral, I guess what I would do is I'd look at this and say this is just a constant. Let's just move it to the outside. Remember we said r and h are fixed values? So that's just a number. I could just move that to the outside. So that means I would have pi r squared over h squared. Right there, that's part of what I'm looking for. Pi r squared. So I feel like I'm moving in the right direction. All right, this would be h squared minus 2hy plus y squared dy. So to solve that integral, remember this is just a number. So I've got h squared times y. This would be minus 2h y squared over 2. Those 2's would cancel, so I'm going to get minus hy squared. And this would be plus y cubed over 3. And I need to evaluate that from 0 to h. Still have pi r squared over h squared. All right, so let me get a little extra space here. So I added another whiteboard so I would have a little more room. So if I plug in an h first, right here, I still have pi r squared over h squared times, plug in an h, I'm going to have h cubed. If I plug in an h here, I've got h squared times h, that's minus h cubed. And plug in an h here, I've got plus h cubed over 3. Minus what I get when I plug in a 0. I'll get 0 for this term, 0 for this term, 0 for this term. And so let's see, h cubed minus h cubed, those add up to 0. So what I really have now is pi r squared over h squared times h cubed over 3. And 2 of these h's would cancel with 2 of these. I still have 1 h left. So I've got pi r squared times h. I'm dividing by 3, so that's the same as 1/3. And there's the volume of a cone. So we have now verified that. What we thought we knew all along is true. Our geometry teachers did not lie to us. All right, so that's what we have for today. So this is our 4th assignment, so assignment number C4, page 464. We're going to do 27, 34, 35, 38, 39, and 49. You guys take care. I know this is strange, but we're going to do the best we can. Stay safe, stay home. Let's all do our part to make sure that we're knocking this thing down and we don't see something bad happen.